start with the solution of state equation. So, solution of state equation. So, we are discussing unforced system. In this we will see a classical approach as well as Laplace transform approach. Now, about the classical approach. So, before going for a classical approach, we have to see why there is need for state equations. Because if you see the classical control, in classical control there is the involvement of only a plant Gs and here R of S to Y of S. So, we are concerning with the output only, but here particularly in state space we are not only concerned with the input output, but also the internal state, that is there is involvement of x1, x2, x3, xn. So, these all the states are important, they are govern the performance, and therefore, how the performance of these states will come, that also need to know. That means till now we have seen that we have to calculate the stability of the system, we have to convert into different form, but along with this there is need to know the state equation of the system. Now, how to calculate the state equations? Now, the plant which we have taken or we have considered, that is x dot equal to Ax plus Bu, y equal to Cx plus Du. Now, when we are concerned with the state equation, that means we are only concerned with the x. So, now here we are assuming the case as we are discussing unforced system, that is we are taking the case that is when this u equal to 0. So, when u equals to 0, we have got a state model as x dot equals to Ax. So, what is the state equations? That is we want to know x of t, that means the equation is x dot of t equal to Ax of t. So, now here x dot we can write down as Ax. Now, this x dot we can write down as dx by dt into A into x. This is a first order differential equation. So, you have already solved this part in in a 12th or maybe in a first year or second year. Now, here this we have to solve. So, how do you solve it? So, we can write down as dx by x A into dt. Now, we integrate these equations dx by x A into dt. Now, here limit we taken for 0 to t, and for this dx let us say x0 to x of t. And now you know the rule of integrations. The rule of integration says logarithm x of x of 0 to x of t into A into t, that is here t minus 0 is equals to A into t. That means the logarithmic of x of t minus logarithmic natural logarithm of x of 0 into A into t. Now, here logarithmic of x of t minus divided by x of 0 equal to A into t. Now, here this has been changed like this, x of t equals to x of 0, this ln can be replaced as e raised to at, and now here x of t equals to e raised to at into x of 0. So, how we have got it? So, what we have done here, x dot we have taken dx by dt equal to x, then this x we have taken this side. So, dx by x a dt, then we have integrated, and here logarithm of x 0 to xt a into t, and then we have solved it, and finally we got x of t equals to e raised to at into x of 0. The e raised to at, the problem is sometimes that how to determine the e raised to at, that is called a state transition matrix. This is called state transition matrix. So, we will see afterward that how to calculate the state transition matrix by various methods, but now here we have got x of t equals to e raised to at into x of 0, that is x of t equal to e raised to at x of 0. So, see here this equation of x of t, if a has eigenvalues let us say on the left hand side of the S plane here. So, that means this a we can write down in terms of lambda, in terms of eigenvalue, that comes a minus sign. So, at t tend to infinity, this x of t tending to 0, that is a stable system. But if same a has eigenvalue on the right side of the S plane, then this x of t may be very higher values, and that is it moves towards the instability. That means from the x of t we can also get the information of the stability of the system. So, that is the state equation x of t, and this equation we have determined the case when there is no u, input is 0, unforced system, there is no force is involved. So, this E of t we can calculate as I plus a into t plus a square t square factorial 2 a cube t cube factorial 3 like this, that is e raised to at. So, once we get e raised to at, then multiplied by x of 0, that is initial state, we can easily get the values of x of t, that is called state equations. Now, we see another approach by which we can determine the state equation, because this earlier approach we have seen that we have to calculate e raised e of at, that is I, we have to multiply a square factorial 2. So, this is quite a cumbersome process, or calculation wise difficult. As the order increases, calculation is more, and we have a very good tool, a Laplace transform, which is used for various applications. So, we will see can the Laplace transform helps in getting the state equation. So, we start deriving it. So, our original equation is x dot equal to ax. This is a linear system, we can call as linear system, and now this is also called as unforced system. Now, our purpose is to get the x of t. So, what we do, we can take the Laplace transform of these equations and see whether we are getting x of t or not. So, taking Laplace transform on the both sides. So, here x of s minus x of 0 a into x of s. Now, here we take x of s left side. So, here si minus a into x of s, sorry, into x of 0. Now, here x of s to si minus a inverse into x of 0. That is what we have done. We have taken the Laplace transform x of x minus x of 0 multiplied by a, this is x of s. Now, this x of s and x of s we have taken one side. So, we get an I, we have replaced an identity matrix because we have to consider with a. So, si minus a into x of s equal to x of 0. Now, this si minus a we have taken on right hand side. So, the si minus a inverse into x of 0. Now, we have to take the inverse Laplace transform. So, taking inverse Laplace transform of our equation. So, if you take the inverse Laplace transform of equation, we will get it as x of t, that is equal to Laplace inverse of si minus a inverse into x of 0, and this we can write down as Laplace inverse of phi of s into x of 0, and this phi of s is nothing but si minus a inverse, and which is called as resolvent matrix. RESOLVENT, resolvent matrix phi s. And earlier we have determined this x of t equal to into x of 0, and now this E of AT we can write down as Laplace inverse of SI minus A inverse. That means this e raised to power at, which is very important in getting the state equation, can be determined by SI minus A inverse, and hence this x of t we have e raised to at, and we have to see what are the initial conditions. Let us say this initial condition may be 1 0, say 1 0 we have to consider, and we have to multiply it by this, and we can get the value of x of t. That is the state equation of the system. So, here state equations can be determined by means of Laplace transform or by means of conventional approach, but we will find that as the order increases, this Laplace transform approach is quite convenient. Now, we start solving one example. Let us say A matrix is given as 0 1 minus 6 minus 5 and x of 0 initial condition is given as 1 0. Actually your plant is like this, x dot equals to x, and we are talking about state equation where there is no input, therefore this is 0 into u. Therefore the example which I have taken, it is only mentioning A and x of 0. Now we have to calculate the x of t, and here we will going to use a Laplace transform approach. So, now the first step is we have to take SI minus A, this SI minus A equal to S minus 1 6 S plus 5, then we can write down as adjoint of SI minus A, because we need to determine the inverse. So, how to get the adjoint of SI minus A? So, we have to take the transpose of the cofactors. So, cofactors are S plus 5, here is S, here is minus 6, here is 1, here is transpose, divide by it the determinant of, okay, this is adjoint. Now, we have to calculate the determinant. The determinant of SI minus A equal to a square plus 5s plus 6, and our main purpose is to determine the SI minus A inverse. Therefore, this SI minus A inverse equal to S plus 5 1 minus 6 S divide by the determinant a square plus 5s plus 6. So, now this equation can be written as SI minus A inverse S plus 5 divided by S square plus 5s plus 6, here 1 divided by S square plus 5s plus 6 divided by minus 6 S square plus 5s plus 6, and lastly S divided by S square plus 5s plus 6. But our problem is basically we want x of t is equals to Laplace inverse of SI minus A inverse into x naught. That means we want final equation in time domain. Therefore, although we have got SI minus inverse, but that is not sufficient, we want to determine the x of t. So, in order to do it, we have to determine its inverse Laplace. So, here we have got 4 functions 1, 2, 3, 4. We have to consider this function individually and then try to determine the inverse. So, therefore, first we take first function as s plus 5 s square plus 5s plus 6. This equation can be written as A divided by s plus 2 plus b s plus 3 So, now we solve it. So, we will get s plus 2, s plus 3. Now, here a multiplied by s plus 3, b multiplied by s plus 2. See here these equations. Now, we compare this and this. So, we can write down as s plus 5, a s plus 3 plus b s plus 2. Suppose if you replace s equals to minus 3. So, if you replace s equals to minus 3, this becomes 0 and we can get the value of b. So, we can write down as this is 2 b minus 1. So, we can get as b equal to minus 2. So, we got b equals to minus 2 by means of this. Now, the next step what we have to do? We have to replace s equals to minus 2 here. So, when we replace s equals to minus 2, that means the part of b will cancel, you can get the values of a. That means s plus 5, a, s plus 3 to b, s plus 2. So, we replace s equals to minus 2. So, you can get it at 3 a into 1. So, a equal to 3. Now, if you see this part, this particular part, this will be represented in terms of a and b. So, here we will get the equation of say s square plus 5. So, s plus 5 divided by s square plus 5s plus 6. So, this is 3 by s plus 2 minus 2 s plus 3. Now, if we take the inverse Laplace of this, so we will get it as 3 into e raised to minus 2t minus 2 e raised to minus 3t. So, this part, this is we have determined for these particular functions. Now, we can determine for this, this and this. So, similarly, we can write down as 1 by s plus 2 s plus 3 that is equal to 1 upon s plus 2 minus 1 by s plus 3. So, you will find that if you solve it 3 minus 2 1 by s plus 2 and s plus 3. Now, we have to take the inverse Laplace transform for this, we will get e raised to minus 2t minus e raised to minus 3t. Similarly, for this part we can write down as minus 6 divided by s plus 2 s plus 3, we can write down as minus 6 s plus 2 plus 6 s plus 3. So, here we will get it as minus 6 e raised to minus 2t plus 6 e equals to minus 3t, and lastly this s divided by s plus 2 s plus 3. So, we can write down as a divided by s plus 2 b s plus 3. Now, here we can write down as a into s plus 3 plus b into s plus 2 divided by s plus 2 s plus 3. Now, if you compare it s a s plus 3 plus b s plus 2. So, after solving this equation, that is replacing initially s equals to minus 3 and afterward s equals to minus 2 here, and we will get it as a will get it as minus 2 and b will get as 3. Therefore, this s divided by s plus 2 s plus 3, this can be written as 2 minus 2 divided by s plus 2 plus 3 s plus 3, and if you take the inverse of this, the inverse Laplace transform of this, minus 2 e raised to minus 2t plus 3 e raised to minus 3t. So, now we have considered the all individual transfer functions, and now we combined in a one matrix and then we multiplied with the initial conditions. So, we can write down the complete matrix as 3 s plus 2 2s plus 3, then here minus 6 s plus 2 plus 6 s plus 3, and here we can write down as 1 by s plus 2 minus 1 by s plus 3, here minus 2 s plus 2 plus 3 s plus 3, and finally we can write down as 3 into e raised to minus 2t minus 2 e raised to minus 3t. About this, minus 6 e raised to minus 2t plus 6 e raised to minus 3t, then here e raised to minus 2t minus e raised to minus 3t, then here lastly this minus 2 divided by s plus 2 we can write down as minus 2t plus 3 e raised to minus 3t. But here this particular portion is nothing but e raised to at. But now the total final state equation is based on our initial condition, that is e raised to at multiplied by x naught. Now here this x naught is given as 1 naught 1 0 1 0. Now we have to multiply this part with 1 0. So what will happen here in this case, this elements in the second column will not exist because of this initial condition. That is finally we will get the value of x of t equal to 3 e raised to minus 2t minus 2 e raised to minus 3t minus 6 e raised to 2t plus 6 e raised to minus 3t. That means in this example, because of 1 0, because we multiplied this 1 0 with this, so this multiplied by this and this portion becomes 0, even this is 0, remaining only this part. If your initial condition is like x 0 equals to 1 1 1 1, then all will be, there is the addition of this and this and this, and we will get the x of t. So now this is the state equation for the unforced system, that is no force has been applied, and we will find that we have calculated this very easily. But the practical problems involve applied force, and in that case how to get the values of x of t. And as I told you that here complete the performance is not depend on only on y, it depend upon x t. Just like in a medical problem, whatever the result, it depends on what are the internal parameters, just like blood test, urine test, all the testing we are doing. Here also these are the states of the system, current flowing the inductor, voltage across the capacitor. So that state information, or as the time changes, how the xt will behave. So here these calculations we have done only for unforced system. So in the next time but we will see how to do the calculations of the state equation when there is an involvement of the force system. That is, next part is concerned with x dot equal to ax plus bu, y equal to cx plus du. If this is the plant, how to calculate the x of t, because when this is the case, there is a part consisting of u. So how the u will act in this case? So we will see these things in the next part. Now these are some references: Ajay Nagarath, M. Gopal, D. Rajobri and B. Sikhu. So you can use these references for detailed studies. Here are the example which I solved only for second order system. Now you can solve many more examples, and you can solve this example by both the approach. You can determine e raised to at by I is at a square t square factorial 2 like that, or a Laplace transform. And again you see that which method is simple, or if you take any example, do the calculation, see that where will get the less computation time. And moreover, we require to determine the inverse. So for the second order system, till second order, you can go for adjoint and determinant, but if you go for higher order, the Leveler algorithm seen earlier, that can be also useful to use. Thank you.